Hello, my name is Kevin Sherman. I am a professional engineer licensed in 17 states in the U.S. I am also the Director of Engineering and Regulatory Affairs for Septitech Incorporated in Lewiston, Maine. I am passionate about high-strength wastewater. I would like to begin this talk with a caveat. Toxins trump strength. If toxins are present in significant concentrations, what I am teaching now will not work. Examples include mortuary wastes, portable toilet wastes, RV dump sites, and many others. If you are interested in one of these subjects, please leave a note on the class evaluation. If there is significant interest, we may include the topic on a future lecture. But for now, let's limit our discussion to microbially available wastewater. So, what is high-strength wastewater? In a nutshell, it is a wastewater that exceeds commonly accepted concentrations for domestic wastewater for at least one strength parameter. Those parameters are biochemical oxygen demand, total suspended solids, fats, oils, grease, called FOG for short, and total nitrogen. We will go into more detail about how each of these parameters is measured in a laboratory in a moment. But because I define high-strength waste as outside of our expectations, our next task will be to state what concentrations our domestic wastewater is expected to have with regard to these four parameters. Typical domestic sewage contains BOD, TSS, total nitrogen, and FOG in these concentrations. The sources of this information are the Metcalf and Eddy textbook entitled Wastewater Engineering, US EPA manuals, and my experience. The threshold concentration for high-strength fats, oils, and grease is not found in many regulations. Typical domestic sewage will have all four parameters close to or less than these concentrations. But if just one of these parameters are substantially above the expected concentration, that result by itself classifies the waste as high-strength waste. So, accordingly, there are many different kinds of high-strength waste. Here are some examples of facilities expected to generate high-strength waste. We expect a vet clinic to exceed just this one parameter. Highway rest areas typically generate very high total nitrogen wastewater through urine. The example most people think of for high-strength wastes are food service establishments. But there are several kinds of food service establishments with special concerns for each. For example, the solution for a bakery would not be appropriate for a drive-in burger and shake place. Most food service establishments are characterized by having high levels of biochemical oxygen demand and fats, oils, and grease combined. So the treatment proposal for treating a restaurant's wastewater would be totally different than one for treating the wastewater from a highway rest area, even though they are both considered high-strength wastes. And this is by no means a complete list. There are many more examples than these, ranging from retirement communities to factories. You may be wondering, can a home generate high-strength waste? I get this question a lot, so I'll answer it right up front. Absolutely it can. It all depends on the activities occurring inside the home. This slide provides just a partial list of the omissions and commissions that can make a home's wastewater high strength. One that I missed, in a home daycare setting, you can also get FOG concentrations in excess of domestic levels due to the excessive wipes being flushed down the toilet. Next, let's explain how a laboratory measures these strength parameters. I want to demystify these procedures so you will understand them better. Biochemical oxygen demand is a measure of the oxygen used to break down organics in the wastewater. The test begins by measuring the dissolved oxygen found in a sample. The container is sealed airtight and placed in an incubator at 68 degrees Fahrenheit. No light is allowed in the cabinet during the 5-day incubation period. Then the container is unsealed and the dissolved oxygen is remeasured. Let's say, for instance, the initial dissolved oxygen was 5.85 milligrams per liter at the start. When it is remeasured 5 days later, it now is 3.45 milligrams per liter. The amount of oxygen removed from the sample, namely 5.85 minus 3.45, or 2.4 milligrams per liter, is the demand microorganisms living and growing in the sample placed on the water. Because microbes reproduce quickly, populations can double in number every 15 minutes to every 6 hours, depending upon the organism. In 5 days, which is 120 hours, one organism grows to over 1 million to quadrillions. From now on, when you hear the term biochemical oxygen demand, I want you to replace it with the more easily understood term microbial tastiness. A sample may not be tasty because it lacks growth factors, it's a thin gruel, or because it is toxic. The device at the bottom of the slide is a dissolved oxygen meter used for determining BOD. A water sample is filtered through a pre-weighed standard glass fiber filter by vacuum. Let's say you weigh a new dry glass fiber filter, and a microscopic photograph of one is shown in the lower right-hand corner of this slide. To do so, you have to use a very accurate Mettler scale. When this is accomplished, the filter weighs 2.56873 grams. Now take a liter of water and place it in a funnel above the filter. Turn on the vacuum. When all the water is pulled through the filter, remove it, dry it, and reweigh that filter. The increase in filter weight is TSS, or total suspended solids. Record the milligram weight increased per liter of sample filtered. That would be milligrams per liter. The dried filter is reweighed, and now it is 2.63473 grams. The TSS is the remainder of these two, 66 milligrams per liter. From now on, when you hear the term total suspended solids, I want you to replace it in your mind with the term murkiness of the liquid. From left to right, a sample of septic tank effluent, the black material, a sample of mixing zone effluent from a recirculating sand filter in the middle, and finally to the right, the discharge effluent from the recirculating sand filter shows progressively less TSS, less murkiness as the liquid goes through treatment. Fog, also known as fats, oils, and greases, are similar in that they are all lighter than water. Fats and oils are two types of lipids. They are chemically similar in that they are lighter than water, are attracted to other lipids, but are repelled by water. That term means oleophilic and hydrophobic. Fog samples are collected in the field with dark glass jars because fog concentration is sensitive to sunlight. By using a separatory funnel, one is shown on the right, the sample is mixed with hexane and allowed to settle by gravity. The hexane and the fog partition in the upper straw-colored layer of the separatory funnel. Open the stopcock and let the reddish, heavier liquid drain out. Then halt the flow by closing the stopcock just as the straw-colored liquid is reaching it. Pour the upper layer into a pre-weighed container. Then, under a fume hood, the hexane evaporates, leaving the fats, oils, and greases behind in the container, which now weighs more. Fog, then, is a measure of floatable substances lighter than water. The keys to treating high-strength wastewater is to first design the capacity to treat the water itself, the hydraulic load, but also a second part is you have to design for the organic load, the BOD, the TSS, etc. So you are very used to using the first half of this, but now I'm going to ask you to add this second part. It will take some math on your part, and you may not be used to doing this, but I'm sure you can do it. What I'm asking you to do is to switch your approach from focusing on concentrations to now focusing on mass loadings. Here in the US, we use pounds for mass. Kilograms are used elsewhere in the world. In residences, the codes that the regulators wrote assumed one strength and concealed that calculation from you. It's like you are used to thinking in only one dimension. I'm going to ask you to realize that systems operate in two dimensions, both the hydraulic and the organic. I say you can do this math because you have done it before without realizing it. Here's a problem that's very common in on-site sewage. Our sewage flow is 450 gallons per day. Our soil loading rate is 0.4 gallons per square foot per day. The question is, what is the size of the soil absorption system? Some of you will instantly know to take the 450 gallons per day and divide it by 0.4 gallons per day per square foot soil loading rate and come up with 1,125 square feet. But there are some questions. For instance, what happened to the gallons per day divided by gallons per day? Well, it went poof. You can make units disappear by having them above and below a divisor. How did the square feet get from the bottom in the soil absorption rate up to the top in the size? Well, dividing is the same thing as multiplying with the inverse of the value. So you flip the value and the units. The inverse of 0.4 is 2.5. I just have one question for you. When did you get so good at algebra? Because that's what this is. I have a confession to make. During my college career, I realized that I did not need to memorize another equation. I could just follow the units to make sure the answer was in the correct units and the math operators were automatically correct. This method is called the factor label method. We need a useful conversion factor to make the switch from concentrations to mass loadings. Here it is. There are 453.6 grams in 1 pound. It takes 1,000 milligrams to make 1 gram, and there are 3.785 liters in a gallon. To get the conversion factor, divide 3.785 by 453,600. The resulting number is very small, but it is not 0. The units associated with the factor is the key. Now, let's put our conversion factor to use and calculate pounds of BOD. We'll notice the equation starts with flow in gallons per day multiplied by BOD in milligrams per liter multiplied by the conversion factor. So we want the answers to be in pound per day. So we have flow has gallon in the numerator. The conversion factor has gallons in the denominator. Above and below a dividing line, poof, it's gone. In BOD, we have milligrams in the numerator, and the conversion factor also has milligrams in the denominator, so poof, it's gone. Now for the last one, we're going to start with liters in the BOD being in the denominator to begin with, and then the conversion factor has it in the numerator, but it doesn't matter the order. Just as long as there's one below and one above, poof, it's gone too. Our answer will be in pounds per day. So in our example, we have a restaurant with 500 gallons per day. The BOD is 800 milligrams per liter. So with our conversion factor, that translates to 3.32 pounds of BOD per day. Now let's compare that to a residence with the same flow, 500 gallons per day, but only 140 milligrams per liter of BOD. Now it's a little over a half of a pound per day, 0.58 pounds to be exact. So the disconnect is that with a loading 7 times greater, this is the problem. This is the heart of the problem. This is why high-strength waste systems cannot be designed by assuming a residential waste strength. This bar chart brings the entire problem into sharp focus. Is it reasonable to assume that if a residential system can operate for years without a problem, which is the leftmost column, that any of these other facilities should have no problem using the same procedure? Of course not. It makes no sense whatsoever. High-strength wastewater has to be pre-treated to have many pounds of BOD, TSS, etc. removed to the point that the wastewater that you're treating resembles domestic wastewater. Then those more typical processes will work.